Greetings and welcome to the introduction to astronomy. In this lesson, we are going to look at a couple of things, and those are dark energy and inflation. And these are two important things that help us to understand the very early origins of our universe and its future. So let's go ahead and get started here. And what we see, first of all, what is the composition of the universe? Most of what we study in astronomy is ordinary matter, and that is about 1% of the universe is visible matter. So that is things that we can see, and that includes things like stars and galaxies and nebulae and those types of objects. Ordinary matter itself is about 5% of the universe. So we can see that here. Um, Most of that is in hydrogen and helium gas. Less than 1% of it is in stars or other items. So the ordinary matter, what we generally study in astronomy right here, is just a small part of the mass and energy of the universe. Dark matter, which makes up a lot of the rest of the matter, is 27% of the universe here. And dark energy is 68%. Again, the vast majority of the universe is this mysterious dark energy. So what we have studied so far in terms of looking at planets and stars and nebulae and galaxies is only a very tiny portion of the universe. We are only looking, with all of these things, we are really only looking at about that 1% of the universe that is visible matter. Now, how has our understanding of this changed over time? And what we have had is that not too long ago, just back in the 1970s, ordinary visible matter was thought to be a larger percentage of the universe. And it was ordinary matter and then ordinary dark matter, things like black holes and other faint stars and things that simply couldn't be seen. So from the 70s to the 80s, that changed, and the ordinary visible matter became only a tiny slice here. And the ordinary dark matter, another tiny slice, and this exotic dark matter seems to be a larger percentage. So the ordinary visible matter over time has become less and less important. And what is this dark matter? Well, we know that it cannot be ordinary matter, because we can study the abundance of deuterium, and that says that ordinary matter is limited to about 5%. So only 5% of the universe can be ordinary matter. The rest has to be some kind of exotic dark matter, as we thought in the 80s, and then dark energy, which took over in the 1990s. So now we have what we thought in the 1970s made up the universe is now just this tiny little piece of about 5% of the material in the universe. So how does this relate to structure formation? First of all, we go back and look at the WIMPs. WIMPs are weakly interacting massive particles, and they are hard to detect. And that is because they only interact through the weak nuclear force. So unlike things that interact through gravity or the electromagnetic force that are a lot easier to find, these are much harder to detect. An example of them would be the neutrinos. These are an example of a weakly interacting massive particle, but these are a very low mass one. So many of these have been proposed to exist, but have not yet been detected. What we need in order for structure to form is dark matter, which has to be something heavy, something with a lot of mass to it. And it would have been needed, otherwise we would not have formed the galaxies and the structures that we see in the universe today on the correct time scale. This dark matter does not interact except through gravity. So it could have started to form structures before ordinary matter. So because it does not interact except through gravity, it is not affected by the electromagnetic force. And therefore it could have begun to collapse earlier, when mass and energy were essentially one and the same. And the ordinary matter, the stars and galaxies that we see today, would gather into these gravity wells and form the structures that we see. And this can explain the filaments and the voids that we see in the universe today. So let's look at a brief history of our universe here. And what we see is, what are the different stages of our universe? Well, very early on at time 0 was the Big Bang. And that is the time of quantum fluctuations and things we really don't know a whole lot about. The next stage was the stage of inflation. And that's where the universe went from being incredibly tiny, atomic size, to being universe size in a very small fraction of a second. And you can see by the time scale here, we are still talking about 10 to the minus 32nd of a second. So imagine the decimal point with all those zeros before it. And that is the tiny fraction of a second during which this time the universe expanded. And then matter began to form. So this is when we began to see protons form, and nuclear fusion began. In that nuclear fusion began to form the elements. So now we're getting up to just the first few minutes. In fact, the first 3 minutes of the universe. We had gone through all of this. The universe had formed through quantum fluctuations, underwent a rapid expansion due to inflation, and then matter began to form, and nuclear fusion created the hydrogen and helium that we see in the universe today. And all that was done in about 3 minutes. Then over the next few 100,000 years, the universe continued to expand and eventually cooled off enough that atoms could form. So once atoms formed and electrons combined with protons to form hydrogen, the cosmic background radiation was released. And then after that, we went through the dark ages where not much happened. This is the stage in between where the microwave background radiation was released and before the first stars and galaxies formed. So nothing much happened there, and nothing much would have been visible. Then we begin to see the galaxies and the modern universe. And then finally, dark energy accelerates the expansion. So the expansion, which had undergone a rapid acceleration here during inflation, had been pretty steady for a long period of time, and now is continuing to accelerate and increase at an increasing rate. So this can explain all of the observations that we see so far. But the Big Bang does have some issues with it that we have to try to be able to understand. And what we see is some of the problems with the Big Bang. First of all, we have two of them that we call the flatness problem and the horizon problem. So the flatness problem first means that the density is very equal to the critical density. And if it was not, then structures would not have been able to form. And what that means is that the universe looks extremely flat. Why does the universe look extremely flat? The other is the horizon problem. Why is the background radiation that we see so uniform? And there are areas that are not in contact on opposite sides of the universe that are now billions of light years apart. So we're looking off nearly 15 billion light years away and heading on opposite sides. That means there is no time for these to have been in contact and to have smoothed out any temperature variations. So these are two things we want to look at and be able to explain. Why is the universe so flat? And why do various areas look essentially the same? So how we explain these is what is called the inflationary hypothesis. So inflation is something that we use to try to explain this. And it's essentially that in an instant of time, the universe grew by a factor of 10 to the 50th power. So a 1 followed by 50 zeros. And this solves the horizon and the flatness problems. How does it do this? Well, the horizon problem is solved because regions that are now distant were actually in contact prior to inflation. So they were close enough together that temperatures could have become uniform, and then they could have spread out. The flatness problem is solved because we are only seeing a small portion of the inflated universe. So in this case, if we want to look at what we're seeing here for the inflated universe, we can look at an example. And here is an example that we see to explain inflation. And that is a balloon. So we imagine a balloon as being the universe. And if we're on a very small balloon as an ant here, you can easily see the curvature. Now, if you imagine that this is a very flexible balloon and you could blow this balloon up not just to a few inches or a foot or so, but do it to kilometers in size, then the ant is still going to be there the same size and is now only seeing a small portion of the universe. And that small portion of the universe will look extremely flat, even though the overall universe is still curved. So we may just be seeing only our small portion of the universe, and the rest of it is simply not visible because there has not been enough time for light to travel from it. If there are parts of the universe that are 15 or 16 or 17 billion light years away, then it will take billions of years before that light can actually get to us. Now, one of the ways we can try to explain this and try to understand what's going on with inflation is through a grand unified theory. And this is a way to try to combine the four forces of nature. And there are four known forces. There is gravity, which is the weakest force. There is the electromagnetic force, and the strong nuclear and weak nuclear forces. And these can be combined together under conditions of very high temperature and very high pressure. Now, we've been able to do this in part here on Earth. And in fact, we can simulate the temperatures that would be needed to combine the electromagnetic and the weak nuclear force. So we have been able to simulate this in large colliders here on Earth. We also have models that can go back and combine the strong nuclear force. So we can get those right. But the problem is gravity. Gravity would have separated out from these very early on, and that very earliest instant of the universe. And in fact, it would have only been within a tiny fraction of a second that all four forces would have been separate. But at this point in the very earliest history, all four forces would have been identical. Now, it may sound strange, but we do see that we can combine, and at certain temperatures and pressures, there is essentially no difference between the weak nuclear force and the electromagnetic force. And we have theories that will combine those with the strong nuclear force at even higher temperatures and pressures that we cannot yet produce. And what we're working on are theories that can then combine this with gravity, which would require even higher temperatures. And we're looking at temperatures of 10 to the 32nd degrees. Now, what we use for this, one of the models that you may have heard of, is what we call string theory. And because these are then different manifestations of the same force, string theory is a way to explain this. And in fact, points of matter are now replaced by one-dimensional strings. So we have these strings instead of a point, instead of a matter being an actual point, as we are used to thinking of here. We used to think of atoms, then we break down those atoms into protons and neutrons. But those protons and neutrons are actually, we think, strings that are actually which are one dimensional. You can imagine one dimension traveling around as in a line here, only having that single dimension. So instead of having no dimensions as a point, they actually have one dimension as a line, and they exist in an 11-dimensional space. And the vibrations of these strings can appear in our universe. So they appear in our three-dimensional version of the universe, or four-dimensional if you want to include space-time. Then they can appear as matter, depending on how they vibrate, or light, or gravity, or any of the other forces. So it's these strings and how they vibrate that make up everything that we see in our universe. And that is a way of being able to explain this. And then the vibrations would be different at different temperatures. So at very early temperatures, at very early times and very high temperatures, we would have had essentially everything would have been one and the same, just these strings vibrating very early on. Now, one of the problems with trying to combine these is that we have to combine two very incompatible theories. We have general relativity, which Einstein gave us to describe gravity. And we have quantum mechanics, which explains uh, the small things, things that are on atomic and subatomic scales. Trying to combine those is very difficult because general relativity gives us exact answers. Quantum mechanics is all based on probabilities. So we want to put these together. And how do we do that? String theory is a way to try to combine these two together. So when we look at things, we have gravity and we have general relativity. And how do we combine general relativity with quantum mechanics? So they can combine together, and it's this quantum gravity, which is really what people are looking for in trying to be able to understand. How does gravity work at the atomic level? And that's something that general relativity does not help us with. And again, that is current research. When will we get that? Some point we may eventually be able to figure out a way of combining these two together and get a really much better understanding of the early history of the universe. So our last section to look at here is what we call the Anthropic Principle. And what that is, the whole idea is that, are we just a lucky accident that we happen to be here? The physical laws are what they are based on how the universe formed. So there's no reason that other universes could not form with other physical laws. And of course, if you have other physical laws, then that could lead to an immediate collapse of the universe. The universe could expand too fast for structures to form. And that means there could be many universes out there that don't have any material in them, that do not have stars or galaxies, or may have collapsed back down immediately. And in some cases, this is what we call the multiverse, which is all of these different universes that would exist. And the Anthropic Principle is really saying that, physical laws are what they are because we are the universe that allows us to be here, that allows us to form because we had the right physical laws. Most other physical laws would not allow a universe to form with things like planets and stars and galaxies. Now, of course, this is just conjecture, since we can't visit and explore these universes. We have no way to get there to explore them. And it is just a conjecture, but it is a very interesting thing to think about. So let's finish up, as we do, with our summary. And what we find here, first of all, is that only a small fraction of the universe is ordinary matter. Everything that we've studied in astronomy is only that tiny fraction. Maybe 1% of the universe is the visible matter that we see. The standard Big Bang model has a few problems. It has a problem with the horizon and flatness. And those are two things that we have to resolve. And in fact, the flatness problem and the horizon problem can both be solved by the inflationary model that says that the universe expanded very rapidly early in its history. And then we look at unified theories as a way to combine the four forces of nature and put them together in a better understanding. And what we're using right now is what is called string theory, as a way to try to put these together, that matter and forces and everything is actually vibrations of strings in a much higher dimensional space. So that finishes up this lecture on dark energy and inflation. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.